morning. We are going to start our part of the course Microscale Transport Process with an introduction in microprocess engineering, which is an interdisciplinary approach, and towards the middle of this lecture we would see how different branches of science has enriched microprocess engineering and which is quickly becoming an effective tool for physicists, chemists, and the engineering issues involved are immense. So, we would like to see how the microprocess engineering, which is a science of enhanced transport process in small devices. Basically, what we are looking at is that when we scale down to micrometer dimensions, this not only changes the length and volume of a device, but it influences the basic physics, inherent physics of the process, and thereby affecting the rates of the unit operations which are prevalent in such devices. Just to give you an overview of the different processes, the time scales involved and the length scale. Mostly in this slide we will concentrate on the characteristic lengths of some of the processes and equipment commonly used in chemical engineering and compare them with the equipments used in microsystems technology. If we look at the top one, let's say when we talk about computers over here, this is of the length scale of about a meter, whereas the computer chip is of the order of few millimeters to centimeters. The electronic structures in those chips are less than a micron. If we think of a chemical engineering equipment such as a starred vessel, then the starred vessel consists of reactors and tubes, whereas on the other hand, if we compare that with microstructured process equipment, they are in the range of few microns to about 1000 microns or so. When we think about, let's say, an adsorbent or let's say a catalyst consisting of pores, mesopores and micropores, obviously the time scale or length scale are quite different from that of a computer or even from an electronic chip. If you think of a basic process, a diffusion process, a diffusive process by which a material goes from one point to another through molecular means, the diffusion coefficient of gases are relatively large, whereas the diffusion length of liquids are of the order of maybe hundreds of microns. So, we go from 1 millimeter of diffusion length, which is characteristic of a gas, to about 1000 or to about 100 microns for that of liquids. When we compare the wavelengths, like we can start with microwave, where the wavelength is few millimeters, and we can go all the way up to X-ray, where it could be even smaller than a nanometer. Some of the common examples which we see in our everyday life: raindrops about 1 millimeter length scale, whereas a cigarette smoke can be as small, the particles present could be as small as less than a micron, which is one of the cause of why it's so harmful. We can also think of the sizes of the mammals, compare that with that of a protein. So, from few meters we come to few nanometers, and also we can think about the small inorganic molecules which are the building blocks of all of us. So, less than nanometer length to about a meter length. So, now when we think of the different processes, the equipments, the processes and so on, what we see here is that the length scales involved are enormously different between a computer and an electronic structure, or between you and the small inorganic molecule which is the building block of our bodies. So, the physics could be vastly different between what is happening on this side of the figure to the processes which become important, the forces which become important on the other side, on the nanometer and micron length scales. And you would see that some of the forces which are important in this region will become almost negligible in the smaller scale, in the micro scale, and some of the forces which are present but not important would probably govern the entire process. An example of this could be, let's say, the gravity force is extremely important in the macro scale, whereas the gravity force or the body force loses its importance when we go towards the micro scale. A surface tension which may not be important in terms of a stirred vessel, a reaction taking place in a macro reactor, but when you think of flow through a micro channel, the surface tension force will start to become play a very important role. So these are some of the basic inherent differences which can happen, which will govern different forces, different processes, and multi-mode physics which are involved when you go from a macro scale to a micro scale. When we would like to give in this course an overview of the effects and the phenomena, for example, in a micro channel which can have characteristic dimensions from 10 to about 1000 micron. And one of the basic reasons why the processes taking place in a micro channel are so fast, or how the miniaturization of the channel size can play an important part in the intensification of the process, in the better yield of products in the process, or for example, to maintain the constancy in temperature in an exothermic reaction, is due to the fact that most of the processes usually in chemical engineering take place within a very thin layer close to, let us say, a solid liquid interface or a solid gas interface. Let us say think about the reaction which is taking place on a catalytic surface. What would happen is, from the bulk, let us say it's a gas solid reaction, solid is the catalyst, and we have two reactants coming with the gas phase, with the inlet gas phase. They will diffuse, reach the solid surface. In the presence of the catalyst, the reaction will take place, a product will form, and the product has to diffuse back to the mainstream to be carried with the bulk flow. Now, this reaction and subsequent back diffusion, all this will take place in a very thin layer close to the surface, which is known as boundary layer, in this case mass transfer boundary layer. We also have hydrodynamic boundary layer and thermal boundary layers. These boundary layers are generally millimeters in the length scale would be about some few millimeters, and most of the transport phenomena takes place in this thin region close to the solid surface. So if you think about the transport process, the rest of the fluid outside of the boundary layer, they do not take part into the reaction or into, let us say, the frictional force or into thermal conduction, into thermal transport at all. So if we could somehow reduce the length scale of the devices down to the size of the boundary layer, then the overall efficiency of the process has to increase. Okay. This is the reason why the microstructured devices or micro devices will have a high value of will definitely work in terms of its transfer length is going to be very small in the scale of the boundary layer, and the higher transport rates which one encounters in these type of devices is a direct result that the sizes are going to be comparable with that of the boundary layer. And you would see the examples of reactions taking place into micro reactors. For example, they will be characterized by rapid mixing. If you have a temperature sensitive reaction, then you would be able to maintain the temperature to a preset level in a much better way if you have such a small system, because your system is of the dimensions of a boundary layer. So it would be easier for you to control, let us say, the temperature, to control, let us say, for example, precipitation of nanoparticles in a system, or to have reactions take place in such a way that the undesirable side reactions can be eliminated, or if not eliminated completely, they can be reduced and the yield of the product will be increased. We'll see more examples of that in the future. So if we have to think about microprocess engineering, let's first start with the macro scale engineering processes, which is process engineering. Now, process engineering can be divided into mainly three parts. One is the simulation or the unit operations, which are the building blocks of any engineering, any macro scale engineering process. There is a renewed thrust on green and sustainable chemistry, which is also affecting, which is also going to affect the process engineering outlook of today's engineers. But the basic aim is to have some sort of a process intensification. The process intensification would increase the efficiency of the process on one hand, also increase the yield of the product, and so on. Now, we would like to integrate the process engineering with microsystems engineering. If we think of the process intensification part, we would like to see how microsystems engineering can play a part in the intensification of the process. So, let's think about the microsystems engineering. Microsystems engineering consists of three parts. One is fabrication, and what kind of materials are going to be used for microsystems engineering. If you think of fabrications, the newer and newer methods of making smaller and smaller devices are becoming available every day, and the materials available to us keeps on increasing, and we can have exotic materials for a very specific purpose. In all these fabrication techniques, newer fabrication techniques and newer materials enable us to integrate different devices, for example sensors, actuators having specific functions. Now, combine these together, the fabrication part and the sensor part together, we have come across a new area of engineering which is known as microfluidics. Microfluidics is nothing but the transport of fluids through micro devices with associated physics, which could be vastly different from the physics that we encounter in macro devices. So, in order to attain process intensification, we look towards microfluidics, which is based on the available microsystems engineering technique, fabrication techniques that are available to us. So, the combination of with the aim of process intensification, microfluidics can be applied, and the branch which has generated out of these two is commonly known as microprocess engineering. Now, one has to also identify that microprocess engineering gets inputs from different branches of science. I have given the example of chemistry over here with, let's say, the catalysts. So, newer and newer catalysts are becoming available with every day, and how do we incorporate the knowledge of chemistry and physics into microfluidics with an aim to intensify the process? That is becoming a challenge, and we are going to meet that challenge, and this has given rise to newer technologies, and specifically that's going to be the thrust of the subject which I am going to cover in this part of the course. So, we would see how microfluidics is going to help intensification of the process, increase the efficiency of the process, enhance the selectivity of a reaction, can maintain temperature equally at all points in a micro device, can work towards a better selectivity for a desired product, and many other interesting applications. So, my building block for this course would be our knowledge in microfluidics, and based on the knowledge in microfluidics and its application in different areas, we would see how a new branch of engineering has been created, and which would probably provide us with better methods to make a specific chemical in the future. Now, if I give you just a brief history of the genesis of micromechanical devices, they have started coming into the literature in the 90s, late 80s and early 90s, which enables fluidic systems, different fluidic systems to be developed. So, we now have microsystems which are present in data processing, in many optical, fluid mechanical and chemical, having many fluid mechanical and chemical functions, and they perform a variety of tasks, okay, from sensing analyzing, controlling the chemical function systems, and producing goods and growing application fields in therapeutics and in diagnostics. Many of us have heard about the word lab on a chip. So, if you think of if you know what is lab on a chip, it has brought a revolution in the diagnostics field. Now, we all have given blood for one reason or another to have certain tests performed by the doctors. Now, it requires certain quantity of blood, usually in the order of a few cc, and a host of reagents, and this process could be very chemical intensive, time intensive, and you will have a large number of different tests to be performed for a specific patient. If we could have, on the other hand, a small quantity of blood which will flow through parallel microchannels, and each of these parallel microchannels will have certain reagents which are packed in it, and as the blood flows through that specific microchannel, that reagent is going to react with the blood and gives a specific signal which can be interpreted to, let us say, it can be calibrated with the concentration of blood glucose or concentration of blood urea present in the system. So, using a tiny volume of the blood and using a fraction of chemicals involved in the process, one would be able to perform an array of different tests on a single chip. So, this has generated interests, and there are many lab on a chip devices which are presently in use and are coming up and will very soon be available commercially, and some of them are already available, in which you can do specific tests with a small quantity of blood and a small quantity of reagents compared to before. So, this will revolutionize the diagnostics as we know today. Now, when we think about why it is so important, so useful, that we again come back to, I think, what I have covered before, that a microstructured process equipment are so much superior to other devices, to macro devices, because of two distinct reasons. One is that the high surface to volume ratio which you would obtain in a micro device, and secondly, this is probably the key words of this course: tiny volumes dominate everything in a micro device. So, not only you are working with very small volumes, milliliters, less than milliliters, 1/100th of a milliliter, and at the same time, since the sizes are so small, the radius of the droplet is so small that your surface to volume ratio is going to be very large. So, some of the forces which were important before will be unimportant for microscale devices, and some forces can become very useful and can control the flow of a fluid, because the surface area is very large compared to that of a volume. So, if we try to organize our thought so far, is that there is going to be difference between the fluid mechanics at microscale and in the macro domain, and we are going to concentrate on 4 specific points to highlight the differences in between the two. The first is going to be the non-continuum of effects. We know that a very common boundary condition that we are very much familiar with in fluid mechanics is a no-slip boundary condition. We know that in most of the engineering, the macro engineering processes, the no-slip condition would be valid. That means the relative velocity between the liquid molecules and solid molecules at the liquid vapor interface would be 0, liquid or gas molecules. Now, this no-slip condition may not be valid if we scale down to millimeter or micron level. So, there will be situations in which there can be slip velocity, non-zero slip velocity present at the interface. This would be even more pronounced when we think of low pressure gases. So, for example, a gas which is at very low pressure, such that the intermolecular spacing or the molecular mean free path becomes comparable to the device size, it is very well possible that the continuum limit may not be valid for such a case, and we are going to have actually a slip at the fluid solid interface. So, the non-continuum effects one has to be very careful about while analyzing the physics of flow inside a microscale device. The same applies to viscosity. What would be the fluid viscosity? How would it vary based on how close to the surface we are, based on how many particles are present in such a system. So, the non-continuum effects, the different flow regimes which are going to be characterized by different types of non-continuum effects would be very important in understanding flow in a microchannel. And there would be surface dominated effects. The surface forces which are probably not very important in a macro scale will start to become important in micro scale. The electrostatic forces, the viscous effects are going to give rise to situations in which we may have flows which are going to be entirely due to electrostatic forces. The viscous forces near a charged surface could be different, and this difference in viscosity due to the charges present on the sides of a solid channel will give rise to interesting effects, which we will cover towards the later part of the course. They are known as viscoelastic effects. So, you would see what they are. Most of the flows which take place in a microchannel are going to be smaller Reynolds number flows or low Reynolds number flows, because it is difficult due to the higher values of pressure drop associated with flow in a microchannel to have very high velocity flow inside such small channels. So, the flow is going to be at low Reynolds number flow, and the approximations that one can make for low Reynolds number flows will be equally applicable, mostly applicable for low Reynolds number for microchannel flows. So, one has to think about how the low Reynolds number effects are going to create some sort of a difference between the fluid mechanics that we know at macro scale and at micro scale. And finally, this is going to be important, as I have described before, the scales are going to be vastly different. Okay. From a meter or a centimeter scale that we are comfortable with, that we know of at the macro scale, we are probably going to the scale of nanometer or micrometer level. So, the devices could be a few micrometer, and in some cases we can have devices which would be whose scale, the length scale could be in nanometers as well. And then we have multi-physics effects, the different forces which are acting inside such a system would give rise to phenomena that can be only explained by a treatment which is going to be a paradigm shift from the treatment that we have encountered so far. So, this multi-scale and multi-physics effects are also going to make certain differences between the fluid mechanics at micro scale and at the macro domain. So, we can say that the micro devices, they are going to tend to behave differently from the objects that we are generally encountered with in daily life. And as I mentioned before, the gravity starts to become relatively unimportant. Surface effect starts to dominate the behavior of fluid in such small system, and the forces, the friction, electrostatic, viscous, surface tension forces due to the surrounding air or liquid, they are going to become more and more important as the device size becomes smaller and smaller. In this, I would like to bring to your attention to a very interesting proposition, a law which is existing for a very long time. It is known as the Squarecube Law, and over the years it has found use in different branches of science and engineering and biology. So, what is Squarecube Law? So it simply says that when an object undergoes a proportional increase in size or a decrease in size, the new volume is proportional to the cube of the multiplier, and its new surface area is proportional to the square of the multiplier. All of us know that the volume is going to increase with L cube, and the surface area is going to scale will be different as L square. So if you think about the surface by volume, it's going to be L square by L cube would be somewhat related to, it will scale as 1 by L. So let's think about an interesting example from biology. Now what you can see is that when suppose you scale up an animal, okay, an ant, and you scale it up 3 times. So its volume is going to be increase, its mass is going to increase considerably, since it's going to be proportional to L cube, whereas its muscles, the cross section of the muscles, are going to increase only by L square. Okay. So its weight is going to increase by L cube, whereas the strength, the muscle strength, is going to increase somewhat, to some extent. It will scale with the square. The scaling factor would be the square of that factor. So its mass would increase by the cube of that scaling factor. As a result, that ant which has been which you have arbitrarily increased its size by its length scale by 3 times, its mass is going to be 9 times, but its strength of the muscles are not going to be, increase in the strength of the muscles are not going to be proportional to L cube. As a result, it's going to have cardiovascular and respiratory functions which would be severely affected. So that's we can have some common commonality with the weight of a person. So if the weight of a person increases, then he or she will most likely going to have cardiovascular and respiratory problems, and also muscle problems, and they are basically due to the reason of the Squarecube law. Now so if we try to express it more scientifically, what we see is that any property which is a function of the area of interaction, it decreases more slowly than properties that depend on the volume. Okay. So if we think of mass, then it's going to scale as L cube, but let's say we are talking about surface tension, which is a function of the area, it's going to vary with L square. So the property which, let's say, is surface tension, and the ratio of that with the mass of the system is going to scale as 1 by L, where L is the characteristic dimension of the micro device. And this has very interesting applications, or the result of this could be very interesting when we think about micro devices. A typical order of magnitude of this ratio of P1, which could be surface tension, and P2, which is something which depends on the volume, which could be mass. So P1 by P2 is going to scale as 1 by L, and for a micro device, if we think of this as a micron size micro device, then this ratio is going to have a ratio of 10 to the power 6 meter square per meter cube. Now if you think of it this way, you would see that when you keep on reducing the size of a device, slowly the surface tension will start to predominate over something, over a force which denotes on the mass. It could be the inertia. So surface tension effects are dominant at these scales when the size of the device is in the order of microns, and there are micro pumps and micro valves which have been fabricated taking advantage of the principle where the surface tension is going to cause or going to make the fluid flow from one point to another, and the inertial effects are rather unimportant. So we can devise of surface tension driven pumps to make liquid flow, or to deliver a packet of fluid from one point to another. So you would see an example of that in subsequent slides. When you think of the applications, this initial application one can think of is in computer components, which is the Winchester type hard disk drive mechanism, where the read write head floats roughly about 15 micron over the spinning disk. So the separation between the two solids, one the head and the other is the disk, is about 50 nanometer, and no matter whatever be the speed of the spinning disk, the flow is essentially going to be a very low Reynolds number flow. It's also, its Mach number is also going to be small. So you have a typical situation in which the Mach number is about 0.3, could be 0.3, and the Reynolds number, even though that the disk is spinning at a very high speed, could be as small as 0.6. Now when you think of such a situation, low Reynolds number, low Mach number flow, even though the velocities involved are very large, since the length scale involved is only 50 to 100 nanometers, these are prime candidates for large Knudsen number flows. And the Knudsen number is defined as lambda, which is the mean free path, by L divided by L, which is the length scale. So here we have the length scale as about 10 to the power of the order of 10 to the power 9 meters, and at some conditions this intermolecular, the molecular mean free path could be of the order of 10 to the power minus 8. So you have a situation in which this Knudsen number could be as large as 10 or even beyond. If that's the case, for values of Knudsen number which are of the order of 10, you are going to definitely not going to work in the continuum limit. You will be definitely working in a situation in which many of the assumptions of continuum limit will not be valid anymore. To give you another example of how these particles, some nanoparticles or microparticles, can be effectively utilized, their motion manipulated from outside so that they can give rise to the working of a pump. It has come in a relatively recent paper in Science. I believe it's in 2002, where it was shown that microparticles of the size 20 nanometers to about 3 micron can be used to fabricate micro devices, micro pumps, okay, which can be used in turn for the control of microfluidic devices. So you have a microfluidic devices in which the flow rate could be microliter, smaller than microliter, in many cases it could be nanoliters. So how do you devise a pump which would create a flow, such a small flow? So one of the novel and innovative examples of use of these microparticles is one can fabricate a self-assembled structures using paramagnetic particles by liquids in microchannel, and their ability to form such a large particle, large structures, and you can control their motion from outside, would give rise to colloidal micropumps and colloidal microvalves. I will give you an example over here. So if you concentrate on the right hand side of the picture, you would see that there are particles which are going to form a string like structure, and you can create the motion of this particle, let's say this particle, in such a way that it's going to as if there is a sine wave which is going through these particles, as a result of which the liquid is going to be pushed from one side to the other in this direction, and small packets of fluid can flow due to the motion, due to the controlled motion of these particles, of these relatively large particles, in this case latex microspheres, through a nanotube, and you can have a flow as low as 0.25 nanoliter per hour. So the motions of these particles can be as small as 2 to 4 micron per second, but interestingly this would give rise to a flow which is only nanoliter per hour order. So if you have a reaction which is taking place and you have to supply reactants in a very small device at a very small flow rate, you cannot have normal pumps, a peristaltic pump or such pumps. Then one has to devise, and this is an example of how to design a pump based on the motion of latex microspheres. This is a graph which tells us about, on the x axis, the values of Knudsen number, and correspond to each of the values of these Knudsen number where we are in terms of the types of motion that's taking place in a device. So, usually Knudsen number less than 0.001, we are going to have 0.01, we are going to have continuum flow. So, from here down, for a value of Knudsen number of 0.01, one can assume its continuum flow. You are going to have no slip condition valid in such a zone, and your no slip your properties are going to be invariant with position. So, if you maintain other conditions the same, the property will not change in such a system. But the moment you go beyond 0.1 up to beyond 0.0 and up to 0.1, then the properties will still remain same, but you have to assume slip flow at the solid fluid interface. So, that is known as the slip flow regime. If you go beyond that, for even higher values of slip flow, for Knudsen number greater than 10, the motion of the species present can be interpreted as free molecular flow, and in between 0.1 and 10 you have a transition where the flow changes from slip flow, but still properties same, to free molecular flow, where the properties are also going to vary with position and time, and in somewhere in between you have transition flow. So, when we think of micro channels, okay, this one, the micro channels over here are generally at the borderline between continuum flow and slip flow. So, the analysis of micro channel flow that you would see, the boundary conditions in many cases will involve a slip boundary condition. So, one has to be careful to find out, based on the value of Knudsen number, whether we can assume a continuum mechanism that is in place, or we have to go to slip or transition flow as well. So, some of the devices which you see here are placed along these two lines, where slowly we go from this which is continuum flow up to the point where the flow is not continuum. And whenever we are working with, let us say, about 0.1 micron and smaller, that is nanotechnology, and on the other side we have MEMS, and in this course we are mostly going to concentrate on this side. What happens to microsystem, the transport phenomena that is taking place in a microsystem, and these are some of the devices which we are going to concentrate on, the physics of flow inside such devices, how to fabricate such devices, the design issues, the engineering issues which are involved in such devices. That is what we would like to analyze in depth in this course. So, to summarize whatever we have covered so far, the relevant issues which are going to be important in this course are: what is the characteristic length and time scale involved in the process that we are designing? What is the transport phenomena which is taking place in such microstructures? Is the phenomenon taking place in the continuum range, or we have to think of a slip flow or a transition flow? The engineering aspects involved in this microprocess, how to fabricate such micro devices. We would also like to know what is the momentum and heat transfer, what's the mechanism of momentum and heat transfer in such devices. Are they coupled? Are the heat transfer and fluid flow, for example, heat transfer and fluid flow, are they coupled together? Do we require an unified solution, or is it possible to obtain the velocity profile from the fluid mechanics part of the problem and then use that velocity profile to obtain the temperature profile in such a system? Or are the processes coupled in such a way that independent solutions of fluid mechanics is not possible? You have to solve both together, which would make the process even more difficult. So, you would see that as well. And finally, we are also going to look at the microfabrication technologies which are available today, which is still evolving at a very rapid rate, and how the use of this fabrication technology results in intensification of any process. That is going to be the goal. So, through all these studies, our main goal is how to intensify the process, how to increase the rate of formation of a specific material in a much more controlled way in a process, and that is what we are going to look at in this course. So, we come back to again what, as I said, the most important line of this course, that the transfer lengths are short, areas are small, but high surface to volume ratios and tiny volumes are going to dominate everything. Now, would like to put a slightly mathematical treatment to this and see what exactly do we mean by that. If your channels are small, then you are going to have shorter transport lengths, which would definitely be beneficial for heat and mass transfer. So, if your if your length scales involved are very small, transfer lengths are very small, then they are going to lead to high transfer rates, and the diffusive mass and heat transport and momentum transport could be very large. And this is a famous equation which relates the property of the material that we are handling, the length scale which is given by x, and the time scale which is given by t. So, let us think of the diffusion coefficient of gases or liquids. They are of the order of 10 to the power minus 6 to about 10 to the power minus 10. Okay. Whereas x, the length scale involved in microfluidic devices, they are of the order of 1 into 10 to the power minus 6 meters, so about 1 micron. So, what you see then is the result gives you a very small value of time scale. So, the transport length could be transport length by diffusive mixing is for gases is 10 to the power minus 6, liquids it is 10 to the power minus 10, and this would give rise to a very small value of the time frequency, the frequency, the time scale of the transformation frequency, and which is connected with the property of the system. So, the diffusion coefficient, the transport length, they govern what will be the time scale of the process, and we can see that the time scale of the process is going to be very small. So, the transformation frequency of such a process is going to be small, which is made clear in the next figure. Now, over here we have the length, okay, and on the x axis we have the time. So, it is basically a characteristic length and time scales for mixing in small devices. Now, when we think of a macro device has a length scale which is typically in the range of centimeters. In the fluid packets with which you can represent the process in a conventional equipment, their sizes are from 100 micron to about 1 millimeters, and the corresponding, if you look at the corresponding diffusion time over here. So, for micro devices we are working in this length as far as the length scale is concerned, and this would give rise to this as our time scale for gases, and for liquids this is roughly of the order of 1 into 10 to the power minus 3, 1 millisecond. So, we are probably working at 10 to 100 millisecond to about 10 into 1 into 10 to the power minus 5 seconds for gases, whereas 1 millisecond for the case of liquids when we think about the micro mixers. For conventional equipments the same things are roughly over here. So, this is the time scale of a micro mixer, whereas this is the time scale of a macro mixer or a conventional equipment. Now, that is what I have written over here. If you think of microstructure devices, their typical length scales from 100 micron to 1 millimeter, and the fluid structures are having lengths of approximately 1 micron. So, your mixing times are shorter than 100 microsecond in gases and approximately 1 millisecond in liquids. So, you can see what is the difference between this for gases and this is for liquids. So, you get roughly about 1,000 times change in the mixing times between a macroscale device and a microscale device. So, this shows why working the main reason for the enhanced selectivity yield ease of maintaining constant temperature in a micro reactor compared to a macro reactor. So, in summary, we can say that the shorter the length, the shorter is the characteristic time for the transport process, and the transformation frequency is going to be higher. And just to give you an idea that what we are talking about in terms of diffusion length is roughly about 7 millimeter in gases and approximately 70 micron in liquids. That's the diffusion length covered by a diffusing molecule in a second. When we try to look at the conduction length, okay, from the basic balance equation, we know that for momentum the conduction length is given by √2 nu t, where nu is the kinematic viscosity and t is the time scale. For heat transfer, the length scale involved is √2 alpha t, where alpha is the thermal diffusivity. So, the characteristic time is proportional, this is important, to the square of the length variation and to the transport coefficient. So, the smaller, if you can keep on making a device size smaller and smaller, the characteristic time is going to be reduced by square of that. Okay. So, it's one can see that how the time required to complete a process decreases drastically once the sizes of such devices are made smaller. So, information about this typical length scale and time scale for fast chemical reactions are necessary in order to compare the processes, and the mass transfer in micro mixers, they act on a length scale which could be a few microns, and the time required would be a few milliseconds or less. So, if we have 3 or 4 reactions, one principal reaction and the other side reactions are taking place in a device, one can control the process in such a way that the slower reactions, the side reactions would be made even slower, and using the less smaller values of the frequency of transformation of such reactions, the main reaction can be made faster. Thereby, the product formed, the yield of the product formed would be much higher, and in such a way the overall yield of the desired product can be increased many times in a micro device. So, that is the direction in which we are going in the design of microreactors. Another important thing one has to keep in mind is what is the scale of the fluid's residence time inside such a device. And within, what we know is that within small devices the fluids are going to rest only for a very short time inside the reactor. Okay. So, if you have a slow reaction, a micro device may not be the ideal option available for you, because the residence time being small, the reaction may not be complete at the exit of the micro device. So, you have to probably generally speaking, it is the faster reactions who are prime candidates for a micro device. So, a slower reaction you probably have to use a conventional method. The faster reactions require very short length of the micro devices. Similarly, if you have an exothermic reaction, an exothermic reaction would be the right candidate for a micro device, because you can control the temperature of the reactant and the products very well in a micro device, since the length scale involved are close to that of the boundary layer thickness. So, for temperature homogenization, a micro reactor would be ideal. So, fast exothermic reactions are preferred over slow reactions in a microreactor for better control and for better conversion of the reactants to the products. And when we think about this is just to look at the enhanced transport that is taking place, enhanced values of the transport coefficient which are available in a micro device. All of us know that the Nusselt number, the constant Nusselt number for a constant wall temperature case, when a fluid flows through a pipe, when the flow becomes thermally fully developed, the Nusselt number becomes constant and is equal to 3.65. And we also know that the Nusselt number is nothing but h d by k, h being the convective heat transfer coefficient, d the length scale, in this case the diameter of the tube, and k the thermal conductivity of the fluid. So, if we are using smaller diameter channels for such reactions, then the value of d is going to be so small, the value of h is going to increase. So, as a result of which you can see that the value of dh, as it reduces, the value of h will automatically increase, since hd by k is a constant. So, this tells us that small channel diameter, the heat transfer coefficient h increases, and this is one example of why we should have a high value of transfer coefficient in a small channel flow. Additionally, we are going to have not straight channels, but channels which are probably bending in this form. So, if we have flow in such a micro channel, then over here there is going to be a lot of lateral mixing, vortex formation, and these lateral mixings and vortex formation will additionally increase the value of h beyond that is predicted by this equation. Okay. So, this is also something which one should look at while designing a micro channel for a heat transfer for any experiment. So, we come back to, but everything comes at a price. Whenever we increase the value of a transport coefficient by making it flow through a small channel, we also increase the pressure loss in a system. So, the pressure loss in a microfluidic system is going to be many times more than that of a macro scale flow. So, how do we provide this excessive pressure drop in micro channel flows? So, you would see that in a micro channel the flow is mostly laminar, the pressure drop per unit length is quite high, and this is one of the limitations of a microscale, effective utilization of microscale devices for fluid transport. So, the high values of h or any other transport coefficient can be offset by the requirement of high pressure drop. So, in many cases we would go for microchannel flows for some specific applications, and I will give you examples of that later on. Now, very quickly I will go through something which you are familiar with, that is the temperature of the fluid flowing through a tube is going to vary exponentially, and where x is the length scale of the device, L is the length scale of the device, and x is the channel is the distance at which it flows. So, if we have flow of liquid through this, then this is your x, and LH could be the diameter of the channel. So, the temperature is going to exponentially change with the distance traversed, and when we connect this characteristic length with the velocity and so on, then this Tx, the temperature change in temperature, can be related to an exponential change with time, and we could see that the characteristic time, which is here in the denominator, it can be connected with rho, the density, Cp the heat capacity, thermal conductivity, but most importantly with the square of the size of the device. So, this simply tells us that with decreasing channel diameter, the fluid temperature exponentially approaches the wall temperature. So, one can have the temperature of the fluid approaching that of the wall very fast if its flow in a microchannel. So, this is another example how the homogenization of temperature can be obtained in a microchannel compared to a macrochannel. So, we need to look at the requirement of efficient heat transfer for high exothermic reactions, and this slide is essentially a summary of what we have covered so far. We know that high surface to volume ratio is responsible for fast heat transfer in microchannels, and additionally we have very high surface to volume ratio, which would be very important, beneficial for surface reactions such as catalysis, heterogeneous catalysis, emulsification or other transport limited processes. And this again tells us something about the time necessary for the time scale involved in unsteady state heat transfer processes. So, a smaller length scale, the characteristic relaxation time also becomes shorter, and we will have a faster reaction taking place. The system is going to reach steady state at a much at a value which is smaller than that of a macro system. Thank you.